So we're in chapter 7 of your chemistry book, and we were talking about electrons and the structure of the atom. I wanted to go over some of my notes. This is review, but things you need to know. So we talked about what was called the hydrogen spectrum. The hydrogen spectrum being, here, let's go up a little further so you can see the hydrogen spectrum being measured by a spectrometer. And we saw pictures of that. And they produced a line spectra. You know, if you take light and you put it through a prism, you're going to get a continuous spectrum like a rainbow, right? Well, they found that they heated up certain elements, certain compounds, certain elements at a high temperatures. They would find that they would not produce a continuous spectrum, but they would produce a line spectra of certain lines. And these lines would always be the same. So for the element, and each element would have a different line spectra, right? And so then they could identify the element by the line spectra when they heated it up, you know? And so they looked through this whole thing and they found hydrogen had a very specific one. And so we'll find that they'll end up studying the hydrogen spectrum. Well, this was found by two different guys. Robert Bunsen is a scientist and Gustav Kirchhoff. And as they got together, they put together this, I should say, let me find out here when they lived. I was going to find out when they lived here. They lived basically in the 1800s to 1860. We're talking about 1860 for that. And going through that, we went on to what was called the Bohr model. And the Bohr model, being the Bohr model, Niels Bohr put together, he took the planetary model by Rutherford. Remember, Rutherford's the planetary model guy. And then he basically said the orbitals, the orbits, you know how Rutherford had, is basically electrons went around the atom in orbits, and each one had its own orbit as it went around. Well, if it did that, they would crash into the center. It would not work. So he said they don't go by orbits, but orbitals. And these orbitals are energy levels, and that they can't get out of that energy level. They're restricted to that energy level without, producing energy, right? And he called these orbitals quantized, or quantum, as you say, and they'd have to stay into these energy restricted orbitals. And there'd be usually way more than one electron. You could have a multiple of electrons in those orbitals. And so from the orbitals came the idea of quantized. And so he put the n would be the quantum number, that's the orbital, times how many basically going into the electrons and quantum numbers, and n being that quantum number. And the example was a ladder, and we saw a ladder. If you have to step up a huge step, the rings are all different, and step up another one, you'd have to have more energy, and basically how the energy state would fall to ground level and go back up, and that would emit energy and light. Because the lowest state closest to the nucleus would be the most stable. So the electron falls back down to the lower energy, and it emits this electromagnetic radiation. Push this down so you can see better. There we go. So the electron E2 minus E1 would be HF, and this would be the lowest state, and the most stable state would be that when it fell down to that lower energy level. But this whole model with the Bohr's model could only be done with hydrogen. They hadn't figured out how they can do it with other elements or anything. So he said it works for hydrogen, it should work for others, but we don't know how it does. And so going on here, so onto the wave model. So Louis de Broglie, and of course de Broglie means French, he basically said that light has properties of particles, but light also has properties of waves. And he took Planck's constant that we had in Planck's constant and developed it into this formula of wavelength equals h over mass times velocity speed. And this would be meant that waves and speed and such had to do with waves, but also particles. And so he called this whole theory that he had the wave-particle duality, meaning, waves sometimes, or light sometimes think that they're waves, and light sometimes thinks that they're particles. But the particles and the waves act together. So particle wave, the wave model. So that's where we kind of left off in the last section. And now we're going to go on to the last guy, and his name is Schrödinger. And he put forth equations. Aaron Schrödinger lived in 1926. He's an Austrian. And he combined the Bohr model, the model up that we learned up here, this Bohr model, with down into Louis de Broglie's, and ended up put together some mathematical ways to calculate these elements, and the elements in calculating quantum mechanical waves and these mathematical harmonies. And when you think of mathematical harmonies, I just think how God has put together this such amazing when you deal with light. And that basically God says, Jesus said that he was light, and Jesus in us, that we're the light of the world. And how complicated it is, but how simple it is really, and how beautiful it is, It's like waves and particles and all these things in each different element and each different atom, and bringing light. We're going to go on to photons and all of this. So let's go back to your book now. So we basically have Schrödinger's equations. So Schrödinger's equations put together, he was an Austrian, like I said, and he proposed the wave mechanical model. Well, mechanical wave, he put together quantum. Quantum, remember, were those wave-like packets in each orbit. You see each one of these have an orbit, but in the orbit, they had a different number of waves. And when these waves basically dropped to a lower energy, they would give off energy so that you can see how much energy it was giving off. So this one here, you'd see, here's n equals 3. So you basically have this one orbital here, but you have 1, 2, 3 waves in that orbital. Same with here. You have n equals 4, one orbital, but you have 1, 2, 3, 4 waves in that. Here's an n5, 1, 2, 3, 4, 5 waves. See how the waves are there? But it says n 4.5 is not allowed. Orbitals having fractional waves cannot exist. So that's what we're finding, these standing waves in the midst. So now Schrödinger is putting together equations for these orbitals are called quantum, right? So let's go on here. A Schrödinger equation can be set up to describe the electrons in even the largest atoms and even in whole molecules. But the repulsion between the electrons and attraction between protons and electrons make equations so complex that guesses and approximations must be made to obtain approximate solutions. So basically, what is he saying? Let me move this up so I was reading it there, but you can move it up a little bit. He's saying that even with his mathematics, it's still not so precise. So basically going on, so such a model demonstrates, it says, Schrödinger's electron equation gives a quantitative picture of electron structure, but something Bohr could not do, because Bohr could only do it with hydrogen. But such a model demonstrates what have been described as mathematical harmonies. I love that. Mathematical harmonies are what God placed in the universe. God has his laws. It's mathematic. Through our finite nature, limits us to imprecise description of the basic unit of matter, the atom. In our study, we should nonetheless acquire appreciation for the design and order that God has used in his creation. I love that. I love that. Going on here, and if you want to read this in the concepts here, where it says understanding quantum mechanics, this guy, I really like what he wrote here in some of the things in the midst of all this. Let's see, quantum theory here. Well, basically, what he's saying in the midst of all of this is that we can say that no one really understands photons and no one really understands electrons. In fact, electrons, are they waves or are they particles? He's saying, are they waves or are they particles? And of course, throughout history, we know that they have basically electrons and photons. They have basically characteristics of both. In 1925 to 1926, they put forth these equations, but our photons, are they packets? What are these photons? You know, are they're arranged like a planets, or are they arranged like fogs or clouds, or how are they? Electrons behave in exactly the same way that photons do. And so as we study photons, we'll find out more about electrons. And we can safely say that no one understands them. And this can be delightful. Have you ever heard of quantum entanglement? And that is so amazing that basically the photons will spin and imitate the spin of each other. So it's kind of crazy, these photons. And so we can say quantum mechanics and all of this is delightful. And Albert Einstein, you know what he said? He basically said that all of this is really spooky science because he didn't understand it yet. So he said, we have a lot to understand when it comes to studying light. And Einstein saying that, probably one of the smartest scientists we know, right? Saying, we have a long ways to go. So let's go back here as I was going over Schrödinger and his principle, the wave model in Schrödinger. And there's something I did not go into here. And this is called the uncertainty principle. And the uncertainty principle is basically put forth as this man here, Werner Heisenberg. And he lived, 1901 to 1976, so not so long ago. And he stated from a purely theoretical standpoint, the uncertainty principle. Basically saying it is impossible to simultaneously determine the momentum, mass times velocity, that's momentum, and the position of electron with precision. Either momentum or position must be precisely measured, but not both. He said, we can't measure both of these things at the same time. It doesn't even work, so we can't do it. So he said, this is his uncertainty. It's impossible to measure. We can measure momentum of it or the position, but not both of them together. So that was a kind of a weird statement, but it applied, didn't it? So he said it was a futile attempt to describe electrons' behavior very precisely because we cannot do this. And so I like what they said here. It says, however, an electron is so small that its speed and position will be changed the moment a photon strikes it. This is not unlike trying to determine the position of a flying bird in the dark by firing baseballs at it. Obviously, the bird's position and speed will be disturbed when it's struck by the baseball. However, some evidence suggests that uncertainty principle is not just a limitation on measurement, but a fundamental characteristic of matter. The uncertain. So we're uncertain exactly where that electron is really going to be, right? It may be that electrons simply do not have precisely measurable positions at all, and the momentum are spread like waves over small regions of space. They don't know. Uncertainty principle holds for all objects, but like the wave nature of matter, it becomes important only for very tiny particles like electrons. So, from that point, from the uncertainty principle, we went into what was called the Born interpretation. The Born interpretation here. And this guy, 1928, Max Born, lived in 1882 to 1970. And he suggested that some solutions to Schrödinger's waves the equation for hydrogen can be interpreted as describing the probability. Now, what he's saying, we're going to talk about probability. Probably the electron will be here. What is the probability that the electron will be here in the midst? So in Born's interpretation, electrons are treated like little points, particles rather than waves, and they are not regarded as having definite orbits at all. So they go through the regions called orbitals. We already had that, right? And an orbital is a region of space in which there is a high probability of finding the electron in that orbital, whereas an orbit is used in Bohr's model is a definite path. So now he is talking about these orbitals, and he commonly represented them as clouds with dots. Like, what is the probability of the electron being at this place in this time period? And so Born's interpretation of the wave mechanical model is sometimes called the electron cloud model. So the electron cloud model. So here we have some pictures here, different views of uncertainty principle. Well, we see here it's uncertain. Basically, the photon, any collision with photon sends the electron careering off into uncertainty, uncertain momentum, that's uncertain. As a property of small particles, a small particle such as electron may actually be spread out like a wave. Is it a wave? Electrons spread out the wave, that's uncertain. As consequent of Schrodinger's equation, it does not allow the position and momentum of the electron to be calculated at the same time. So this picture, probably of finding electron at a given space, is very uncertain, right? That's the uncertain. But now we have, what is Born doing here? He's going to be talking about something else. So he's going to be talking about the probability that it's going to be. We can't figure it out, but probably it will be there, right? The probability and statistics of being in that. And so basically going on this electron cloud model, he put together this electron cloud model. So here is the atom and these are electrons. They're most likely going to make, these areas are going to be closer to the nucleus and these are going to be farther to the nucleus. What probability? And he puts dots at those probabilities. So this is kind of a crazy, but it's called the clouds. And so his interpretation is simply another way to look at Schrodinger's equations. And it's called a probability model, right? And so this electron cloud is just probably the electrons that would be in this area because there's more of them there. And he gives the example like a fast-moving fan. He says, as the fan is going in each blade and it's going so fast, you can't see where those blades are, can you? Because they're turning so fast in this fan. So you don't know where that blade's going to be at a particular position. But you can try to divide it into positions by saying how big the blades are and figuring that out and saying your probability of statistics of that different fan, that different blade being there. So that's all he's saying. But otherwise, it's hard to find. And this is what he's saying is related to electrons. And also the flower and the bee theory is that, okay, there's going to be a lot more bees closer to the flower. And so we can say probability and statistics, you're going to find one there more than you're going to find one way out here, is all that says. So we cannot know how an electron gets from one place to another, nor can we know precisely its position in the orbital relative to the nucleus at any instance, but we have the models of it. So here's the electron cloud model saying, baby, probability, where are they going to be? Probably be here closer. So here's the models that we went through. So the Dalton model was in the 1800s. They just said, oh, everything consists of atoms, and these are these little balls. And then J.J. Thomson put forth the plum pudding model. There's things inside of these balls, basically. And Rutherford went forth and put the nuclear model, saying, oh, there's electrons. Each electron is orbiting like a planet around, right? But then Bohr said, no, it can't be that way. We have orbitals, these sections here, and each orbital will have 1, 2, 3, 4, 5, 6. They'll have a different number of electrons in each orbital at different levels of that going into quantum mechanics, and we'll find that. And now we have the Born electric cloud model here, and that was showing basically its probability and statistics where these electrons shall be, and this was in 1928. So, in the midst of all this, understanding quantum mechanics is a big deal. Let's talk about some of these questions here And then we're going to go on to the next section. So what is meant by the term continuous spectrum? Well, when I think of a continuous spectrum, I think of a rainbow. It's continuous, you know. Light goes through a prism, and then you see all the colors, and they're all connected to each other. That's a continuous spectrum. But when they heat certain metals, it doesn't give us a continuous spectrum, and that way we can tell what metal, or what, I should say, what gas or compound, or actually what element would give a certain spectrum of light, and we could figure out what that element is. It's, so foundational, isn't it? So number 2, tell what contribution each of the following scientists made to the theory of electron structure. And that's in this chapter. We had Bohr. So what did Bohr do? Bohr basically put together that the electrons in the hydrogen model can move only about in specific orbits. And these orbits he quantized, and basically bringing forth quantum mechanics, but basically saying, that they were orbitals. They weren't orbits, they were orbitals, and they could quantize in that. And that was a picture of that ladder. But he only could do this with hydrogen at that time. And then we have de Broglie. De Broglie put together the wave-particle duality. The matter that waves, they do have electromagnetic, as the waves for anything that's traveling at speed, but he put together matter waves and talked about matter waves, and then going on to electromagnetic waves. But also saying that the big thing about him is saying that the wave-particle duality means that basically these electrons have wave and particle together. They are particles and they are waves. That's de Broglie. On to Schrödinger. What did Schrödinger do? He put forth the mathematical equations, putting these two guys and stuff together, and put together the equations that we could figure out this quantum picture of all the other atoms, and not just hydrogen, but other atoms, and put forth his constant in his math. Schrödinger put together the math for it all. And then on to Heisenberg. Heisenberg put together the uncertainty principle, saying you cannot, you cannot test for velocity and mass and onto position. You can't test these all. You will still be uncertain. No one really knows where the electron is, and you cannot do these both at the same time. So uncertainty principle. Okay, number 3, differentiate between the ground state and the excited state of electron in a hydrogen atom. Well, the lowest or closest to the nucleus would be that lowest, most stable place, and especially in the hydrogen atom, it would be close into that state. That would be the state, the equilibrium, where the lowest state with the less energy where that electron would want to go. Excitable states are farther away from the nucleus and at higher positions, and usually excitable states have a loose photon going back with a loose photon in the midst of all that. So how did the line spectrum of hydrogen support Bohr's model of the atom? So how did that support the line spectrum of the hydrogen? Supported Bohr's model by falling back into the lower energy levels, emitting these electromagnetic radiation. So he saw that there was energy between, as the photon was hit and it fell back into the lower energy, it would give off light. So as it falls back, it emits. And then they have, of course, that formula E2, which is the energy, final energy minus the initial energy, and you'll be able to figure that out. So what was the major failure of the Bohr's model? Because he only could really put it together with the hydrogen. He needed to put it together with a lot of different others too. Explain what is meant by the phrase, wave-particle duality. What do you think? Waves are like particles, and waves electrons act like waves, or photons act like waves at sometimes, and waves also in the midst of this, they also act like particles, right? Like particles and waves. So they found out that they had both the nature, even the nature at the same time. Wave-particle duality, two natures. What is the importance of the uncertainty principle as it relates to the arrangement of electrons in atoms? So the uncertainty, it's impossible to determine momentum and position of the electron with precision. So you can't really figure out momentum and precision and find out, how fast it's going and where it's at. It's impossible. So not both. So principle, okay. Differentiate between orbit and orbital. An orbit would be just an orbit like one planet's going through an orbit, right? An orbital is an energy level where there's a lot of different, electrons or those considered little planets or whatever, but they're all going in this whole area, which you would call the orbitals, you'd call quantum. It's basically that packet there of an orbital where all those electrons cannot have their energy level in that level. So I hope that all works out. You understand that all. So the last thing I want to go over here and I think I went through some of this here. There was a little bit here. Put this up here, see if I can get it to stay up there. Okay. Okay, we went over the uncertainty principle. So that's Werner Heisenberg in 1927, impossible to determine mass and velocity at the same time. So that's pretty important. The Born interpretation, not the Bohr. Remember, the Bohr is what we learned before. If we went for the Bohr, we went for this one, right? We talked about Bohr model. But this is the Born interpretation. Max Born in 1928 says basically these electrons are moving in orbitals and they look like little clouds or dots. And he put together the electron cloud model. And this was another way of looking at Schrodinger's mathematical equations. So, and this was a probability, probable that the electron would be at the same time. Now, going on understanding quantum mechanics, electrons, are they waves, are they particles? We have equations, but do these equations, are they foundational? What about these photons, these packets, these in quantum? What are they really? How do they really look? And what are some characteristics of these photons? We don't know. So are they planets? Are they like springboards? Are they fogs? Are they cloud? All these things are pretty important, right? So we can say safely that no one really understands light in its fullest now. In fact, this is very delightful, kind of, because, when you look at quantum entanglement, you'll find that these photons actually communicate with each other. And that's what we're learning now. And Einstein called this whole section of quantum mechanics and light a spooky science, because he said we have so much more to learn. And so here we have, these are that you need to know, the speed of light and the wave times frequency. That's important to know. Energy levels here, and each frequency level, these are actually the formulas that you should be aware of. And so that's about it. So let's stop there.